Okay, there must be an exam or something this week, given the number of empty seats, but thank you all for coming and being dedicated. It's just been brought to my attention that apparently the homework review that I just posted also had a sound issue because this new version of the software likes to randomly mute the sound on me, so I will need to deal with that tonight, so the homework review will be a little bit late this week, but I'll get it done tonight. And other than that, the only other thing I want to briefly bring to your attention is, again, I have expanded office hours this week because of the exam and other things, so check Blackboard for the full schedule. I did have to change some of them around on Wednesday, so I won't be there. I probably won't be there the normal time, but I'll be there after that and possibly a little bit before that. So check the schedule on Blackboard if you need to come see me about anything, and I will be happy to meet with you any of those times. All right, so what we're going to continue with today is moving on through Chapter 7. Chapter 7 deals with energy in chemical reactions. And we sort of, last time what we introduced was the concept of change in energy. So whenever we're sort of still in more of the physics envelope of energy changes. Now we introduced the idea that when you have a delta E change in energy, it's given by the sum of Q and W, where Q is the heat and W is the work. So the two forms of energy transfer are always some combination of those two, heat and work. And we're going to deal mostly in this class with heat, which is Q. We're going to learn today a lot about how to calculate Q and how it plays into chemical reactions to some extent. W is the work term, and this is more commonly encountered in physics context, but we do see it a little bit in chemistry. And the one place where we see work is in the expansion of gases. So we're going to talk more about gases in Chapter 8, the next chapter, so some of this stuff will make a little bit more sense after we've gone through all of that as well. But we should recognize that gases, they don't occupy a fixed volume, so they're freely moving about, and they can expand and contract, expand and compress, as it's called, to different volumes. So when you have a gas, the two important parameters for us to think about now are pressure, which is force over area. So that's kind of the physics definition of pressure, which is one of the important properties of a gas that we'll cover in a lot more detail in Chapter 8. So when gases are moving around in a closed container, they exert a pressure on the walls of the container because they're constantly colliding with that container. So pressure is force over area. And there's a lot of different units for pressure, but the one that we're going to use most frequently in chemistry is atmospheres. So basically, 1 atmosphere is the pressure of the atmosphere at sea level, and we just sort of scale everything relative to that. That's a very common way to do it. And so when you have a gas in a container that's either expanding or compressing, changing its volume, the work is given by the negative of the external pressure times delta V. And so this equation only works when you have a constant external pressure. So this P with a little ext means external, and that's going to be a constant external pressure on the gas. So if we had a piston of gas out here in the front of the room and it was expanding against the room pressure, that would be an external pressure of approximately 1 atmosphere. But the external pressure is basically whatever pressure is on the outside of the container of gas that the gas is expanding against, or that is causing the gas to be compressed if it's going the other direction. And then delta V in this equation is just the change in volume. So as we said, gases can change their volume, either get bigger or smaller. And whenever the gas changes its volume against a constant external pressure, there's going to be work associated with that, and this is how we calculate it. Now a little bit about units in this equation. We'll see it in practice on the next slide when we do a quick example. So if you multiply the external pressure, which is typically in atmospheres, multiplied by delta V, which is usually in liters, the unit that you get is a product of atmospheres and liters, which is not a very typical or very conventional energy unit. So we have to be aware of a conversion factor, which is that the 1 atmosphere liter, or 1 liter atmosphere, is equal to 101.3 joules. So joules, as we already talked about a little bit last time, is the SI unit of energy, or work, or heat, or any combination of those three. And so if we want to convert from atmosphere liters to joules, we have to use that 101.3 as a conversion factor. So thinking about the signs of work then, we said last time in abstract that if work is done by the system, that means the work term would be negative. It's losing energy in the form of work. And if work is done on the system, that means W is positive. That means the system is gaining energy by the surroundings doing work on it. So if we think about the signs of this, if our final volume is greater than our initial volume, that means the gas is expanding. So the gas is starting out at some smaller volume, expanding to a larger volume. If that's the situation, we see from this equation that means delta V is positive. Whenever the gas's volume is increasing, delta V is positive, which means work would have to be negative because there's this minus sign out in front of the product of the two. Okay, so when a gas expands, work is negative, and that means work is done by the system. So in order for a gas to expand, if the container of gas is your system that you're studying, the system would have to do work on the surroundings. So work is done by the system in that situation. And then the opposite would be true if your final volume is smaller. That means we're compressing the gas. So if your final volume is smaller than the initial volume, getting smaller, that means gas is compressed. Delta V would be negative, less than 0, which means that the work has to be greater than 0 in that case because it's a negative times a negative. So that in that case, work is done on the system. So in order to compress a gas, the surroundings has to do work on the system. You have to do work on the gas to be able to compress it. But that comes straight out of the equation, so as long as you're careful about remembering to put this negative sign in the equation and remembering that delta V is final minus initial. Anytime we have delta, remember that means final minus initial. As long as you keep all that straight, that mathematically comes right out from the equation. All right, so then we'll just do one quick example of how to use this. There's not a lot of depth to this topic. So the only type of expansion work we have to deal with is this situation here. So we have a reaction produces an ideal gas, and the volume expands from 1 liter to 10 liters against a constant pressure of 0.978 atmospheres. Calculate the work done. So it doesn't necessarily have to be a chemical reaction. It could just be a physical change. But here we have some chemical reaction that generates a gas. Initially the gas is at 1 liter. And then it does some work and expands to 10 liters. We want to know what's the work associated with that. So there's really not much complication to this. We just take that same equation. W is equal to the negative of external pressure times change in volume. So the external pressure, we're told, is 0.978. So we're expanding against a pressure of 0.978 atmospheres. So that's our P external. So we have to remember to keep the minus sign. And then delta V is going to be just V final minus V initial. So you have to make sure we keep straight which one is final and initial to do this. So it's going to be final initial, so it's from 1 liter to 10 liters. So the final volume is 10. The initial volume is 1. So that means the change in volume is 9 liters. So when we multiply those two together, external pressure, delta V, with a minus sign out in front, we get minus 8.80 liter atmospheres. Now I didn't specify the units for work, but in almost every case we're going to want to do this in joules, not in liter atmospheres. So the work in joules, again we have the conversion factor that I introduced in the last slide, is minus 8.80 liter atmospheres, and then it's going to be 101.3 joules per liter atmosphere. So it's just a simple conversion. We get minus 891 joules. So that means the gas does 891 joules of work when it expands from 1 liter to 10 liters against a pressure of 0.978 atmospheres. So that's about as complicated as it gets for this topic. Any questions on that? All right, what we're going to move on to now is a description of a new state function. So we said that delta E is a state function, meaning that it depends only on the initial and final conditions, and we can calculate it as the sum of heat and work. But it's not the most convenient one for us to use all the time, because if you're doing a chemical reaction in a lab, typically those reactions are done at constant pressure. And so if you have constant pressure, you have the possibility of expansion work, because again, the volume can change during a chemical reaction, so you have to calculate Q and W. So the point is, if you want to calculate delta E, as we said, you need to have two terms, Q and W. So it would be simple, instead of having to do two measurements, measuring heat, measuring work, and then combining the two, if there was some new state function that only required us to make one measurement. And if we're doing chemistry at constant pressure, we can do some rearrangements here and get a new state function that's a lot simpler for us to use. So we have to recall from what we just learned that work is equal to negative external pressure times delta V if we have a constant pressure process. So it has to be at constant pressure for this to work. And we can just sort of rewrite this as minus P delta V. So as long as the external pressure is constant, there's just one value of pressure we have to worry about. And then the Q that we're going to measure, because we're measuring it at constant pressure, we're going to abbreviate that as Q with a little p next to it. So just QP just tells us that we're measuring heat at constant pressure. That's all that's telling us. And so if this is a situation, we're conducting everything at constant pressure, we can rewrite delta E then. So delta E at constant pressure if we have constant pressure process, we can write this as QP, and then the work we can rewrite as minus P delta V. Okay, so we're just making some substitutions here. Heat is just putting a little P next to it to indicate that we're talking about constant pressure specifically. P delta V for work, or minus P delta V, as long as we're at constant pressure. This is a rearrangement or another form of the equation that works. So then what we're going to do is we're going to solve for QP. So QP is equal to delta E plus P delta V. And what we're going to call this term QP is a new state function. So we see that QP is the sum of two state functions. Remember, state functions are functions that have delta in front of them, is sort of the simple definition. So if Q is the sum of two state functions, delta E and P delta V, it can also itself be a state function. We abbreviate that as delta H. All right. So if we have a constant pressure process and we measure the heat, we get this new state function delta H directly out of that. So delta H for a lot of chemical reactions is a much more convenient one to think about because we don't have to measure Q and W, we just have to measure the heat, and that gives us delta H directly. So what H is referred to is called enthalpy. And taking the deltas out of the equation, it equals energy plus the product of pressure and volume. Okay? But again, the important thing here is that delta H, the change in enthalpy, is given by the heat that we measure at constant pressure. So the whole idea here is that delta H is a new state function that we have now to classify chemical or physical changes, but it only depends on the heat. It doesn't depend on heat and work together. So if we conduct a process, in our case is usually a chemical reaction, but it could be a physical process of some sort. If we conduct it at constant pressure and we measure heat for that, which we're going to learn how to do today, how to calculate or measure heat, if we do that, we're going to directly get delta H out of this. So delta H is a new state function that we're going to use. Now you might be thinking, well, does this have any value for us? We think, delta E is a pretty valuable state function because it tells us how energies are changing between reactants and products, which is usually because of different bond energies between the two. So does delta H have any real value for us? And so what I'm going to do here is sort of compare the two and see, how similar are they to each other, how different are they from each other, and whether or not this delta H is actually useful for us. So again, as we just said in the last slide, delta H can be written as delta E plus P delta V. So if we have reactions that do not involve gases, so just about all the reactions we talked about in Chapter 6 happen in aqueous solution. So if it's a solution reaction or a reaction involving solids primarily or liquids, no gases involved, volume changes are typically very small for those types of reactions. All right, so if we run, and maybe you've already done some of these in the chemistry lab part of this course, if you do a reaction in aqueous solution, the volume of the solution doesn't change very much during the reaction. It's basically the same before and after. And so because of that, when you have these condensed phases like liquids and gases and no gases involved, this P delta V term is pretty close to zero. Okay? Because if the delta V is very small, the product of P and delta V is also close to zero. And that means in these situations, delta H and delta E are basically identical to each other. So even though delta H is a little bit simpler to measure because it only depends on heat, it doesn't depend on heat and work, it turns out the magnitude of delta H ends up being almost the same as delta E. Now we can also have some gas phase reactions as well, and if we think about how these ones work, if the moles of gas do not change, so as an example, let's say we're doing this reaction in the gas phase. Let's say we take hydrogen as a gas, react it with chlorine as a gas, and make gaseous hydrogen chloride. So this is, again, all gas phase reaction, no solutions or liquids involved in this case. If we do this reaction, we see that on the reactant side, we have a total of 2 moles of gas, 1 mole of H2 and 1 mole of Cl2. On the product side, we also have 2 moles of gas, 2 moles of HCl. So in a reaction where the moles of gas doesn't change, this will also make more sense after Chapter 8, but that means this product, P delta V here, is equal to 0. So if there's no change in the number of moles of gas, there's also no change in the product of pressure and volume. So that means in this situation, delta H is equal to delta E, because this whole term here goes away, and the two become equal to each other. So for some gas phase reactions, if you're not changing the number of moles of gas, then you're going to have delta H and delta E being exactly the same. And then if we have reactions where moles of gas do change, so let's say we do the oxidation of carbon monoxide to carbon dioxide, so we have carbon monoxide plus O2 gas, making 2 CO2. In this equation here, we have 3 moles of gas on the reactant side, 2 moles of CO plus 1 mole of O2. On the product side, we have 2 moles of gas, 2 moles of CO2. So the number of moles of gas is not the same on both sides of the equation. So that means in this case, the pressure delta V term will not be equal to 0, which means that this is the one situation where delta E and delta H definitely won't be the same as each other. So if you're changing numbers of moles of gas, you're going to have slight differences in the values of delta H and delta E. As it turns out, though, in most situations at the scale that we work with and the typical pressures and volumes that we deal with, this P delta V term is significantly smaller than the heat term QP. So even in this situation, delta H and delta E are not all that different from each other. They're not quite as similar, but they're not exactly the same. So the whole point of this is that even though delta H and delta E aren't always exactly the same, and even though they're defined differently, the values that you end up getting when you measure them end up usually being very similar to each other. So in many cases, we actually use them interchangeably. I mean, they do have specific, precise definitions that you should be aware of, and slight differences in how we measure them that we'll go through a little bit. But in reality, both of these just refer to the amount of heat that's involved in a chemical reaction. So if you have reactants and products, and you're either absorbing heat to do the reaction or releasing heat as part of the reaction, measuring that heat gives you delta H if you're at constant pressure, and really that's a pretty good approximation of delta E as well. Okay, so that's kind of what we mean by delta H. So then let's think about some properties of delta H now, and the two major ones are whether it's endothermic or exothermic. So delta H can be positive or negative. If it's negative, that's going to be called an exothermic process. So if you have an exothermic process, that means heat is released as sort of a product of the reaction. It's not really the rigorous way of thinking about it, but what you can think about is in an exothermic process, heat is released as a product. So, for example, if we burn hydrogen, we should be familiar with burning anything, but hydrogen especially, because it releases a lot of heat. So if you take hydrogen and oxygen and burn them together, you'll make water as a product, and as we should be familiar with, you'll also release, these are all gases, not that it really matters, but you'll also release a lot of heat. Okay, if I were to take a balloon of hydrogen and set it on fire up here, it would make a big boom, right? And that's a lot of heat being released. So you can think of heat in an exothermic reaction as being a product. So burning things is sort of the classic exothermic reaction where you release a lot of heat to the surroundings. Another one that I'm showing here is if any of you spent significant parts of your life in colder climates, they have these hand warming little packets. So I used to work at a symphony hall and stand at the garage entrance where it was 0 degrees for 3 hours while I was standing there because it was in Ohio. And so I'd hold these little things in my pocket to keep my hands warm so that I didn't die, basically. And so these are these little packets that have it's basically a redox reaction, if you're curious what that is. There's a redox reaction that goes on inside of here, and it produces heat. It's an exothermic reaction, so that heat gets transferred to your to your skin, to your hand, and keeps you warm. So an exothermic reaction is one that produces heat, and what that means is that the temperature of the surroundings will increase. So when you're conducting an exothermic reaction, that heat that's released is going to go to the surroundings. It's going to be absorbed by the surroundings and cause them to increase in temperature. Okay? Endothermic is then the opposite, exact opposite of this, would be when the heat is greater than 0. So when delta H, or the heat measured at constant pressure, are greater than 0, that means heat is absorbed and can be shown as a reactant in some sense. Again, it's not really a reactant. Heat is not a chemical substance, so it's not rigorously correct to show it as a participant in a chemical reaction, but we can think of it this way at least. So heat can be think of as a reactant in a chemical equation when it's endothermic. So if we take ammonium nitrate as a solid and solid ionic compound, and we add it to water to make aqueous ammonium nitrate, this ends up requiring us to absorb a bunch of heat. So the process of dissolving ammonium nitrate ends up absorbing heat from the surroundings, and so we can think of heat as being a reactant or as a participant in the reaction that we have to add into it to get this to happen. So these, I don't know if they use ammonium nitrate, but it's some similar process. They have these instant cold packs that don't require you to freeze them, that you just basically break off a little thing on the inside, and induces some sort of endothermic process of dissolution or reaction. So if a cold pack being the opposite would be one where heat is going from the surroundings into the reaction, so the temperature decreases. So for an endothermic reaction, the temperature of the surroundings will decrease in that case. And that's because in that situation, the surroundings are donating heat to the chemical reaction, and so it's losing that heat, and temperature will go down as a result of the surroundings. Okay? So any questions on the difference between exothermic and endothermic? So we can perhaps think of this, maybe a little bit helpful would be to think of this pictorially, using sort of these qualitative energy diagrams. So if we have an enthalpy scale here, if we have an exothermic reaction, which I'm showing on the left here, remember exothermic means that delta H is less than 0. So whenever you see exothermic, you know that the sign of delta H is less than 0. Remember that delta means final minus initial. So if we're considering a chemical reaction, our initial state is the reactants, our final state is the products. That's final, initial, and final. And so what that means is that if delta H is less than 0, that means our reactants have higher enthalpy than the products. We don't usually think about absolute enthalpy H, but if we wanted to here, in an exothermic process, delta H is going to be the enthalpy of the products minus reactants, so in order for it to be negative, reactants have to be higher than products. So during an exothermic reaction with delta H less than 0, reactants have higher enthalpy than products, and during the process of the reaction, heat is released from the system, so you get heat out, and that's where the temperature of the surroundings will then increase. Endothermic is opposite, delta H greater than 0. So if in this case, because delta H is greater than 0, that means the products have higher enthalpy than the reactants. The final state is higher than the initial state whenever the change is positive. So products are higher enthalpy than reactants, and our delta H would then be greater than 0. And in order for this reaction to happen, heat goes into the system, which is why the temperature of the surroundings would decrease in that case. Okay? So that's sort of the difference, again, just another way of thinking about it, between exothermic and endothermic processes. And for chemical reactions especially, we think of the initial and final states as being the reactants as the initial state, products as the final state. And so any delta H is going to be reflected as differences in enthalpy between reactants and products, which of course can be positive or negative, as we just talked about. All right, questions on those concepts? So what we're going to move into now then is a more sort of practical approach for measuring heat and measuring enthalpy changes. So we're going to talk now about the equations that we use to measure heat, and then a little bit about the experimental laboratory process we would use also for doing that. So if we're thinking about heat being measured, as it's transferred between system and surroundings, there's sort of a proportionality that emerges. So we can kind of think about this logically for a little bit. So if we take, remember we talked about the example last time when we were sort of introducing the concept of heat. If we took a container of boiling water and put it on the table here, eventually that temperature of the water would decrease to room temperature because it would transfer all of its heat to the surroundings, either to the table itself or to the air surrounding it or some combination of those two. So we understand sort of heat transfers being whenever two objects at two different temperatures are in contact with each other. So if we think about this for a second, if I put a glass of water up here, that was at boiling temperature, and let it sort of transfer heat to the surroundings and equilibrate, or if I put a huge, let's say 1 gallon container of water up here and let it do the same thing, which one do we think would transfer more heat, the smaller one or the bigger one? I think you're thinking too hard about this. It's the bigger one, right? So the more substance you have that's transferring heat, you're going to have more heat. So heat is proportional to the mass of the substance that you have. So if you're transferring heat between two substances or two objects, wherever the situation is, the more of that substance you have, the more heat it will transfer under otherwise identical conditions. So a cup of boiling water is going to transfer less heat than a gallon of boiling water. Or maybe think about this a little bit more clearly. Instead of putting the boiling water here on the desk and just sort of watching what happens, if I were to dump boiling water on you, which one do you think would cause more damage? I wouldn't do that. A thimble of boiling... I'm not going to even dump a whole glass. That would be bad. Let's do like a thimble of boiling water or a gallon of boiling water. Which one would transfer more heat to you? The gallon, right? So I think hopefully now it makes sense. But I won't do that to you. Don't worry. I'm not a violent person. And then the other one that's maybe a little bit hard to think about but should make sense conceptually is that if we think about how much the temperature changes during the process. So if we put a glass of boiling water up here, it would start at 100 degrees Celsius, and then eventually it would get down to the room temperature, which is around probably like 23 or so Celsius. So if the change in temperature goes from 100 to 90, that's going to be some amount of energy transfer, right? Heat transfer. And then if it goes from 100 all the way to room temperature, that's a different amount of energy transfer. And which one of those do you think is larger, the small temperature change or the big temperature change, which represents a larger amount of heat being transferred? The big one, right? So the more the temperature changes, the more heat has to be transferred for that to occur. So we also know that heat is proportional to the change in temperature. So whenever you're measuring heat, either for a system or for surroundings, the more the temperature changes, the more heat that was involved in that process. And as we sort of talked about a little bit earlier with another equation that we did, I'm trying to think of which one now, but if we have Q is proportional to two things, it's proportional to mass, it's proportional to delta T, it would also then be proportional to the product of those two. So heat is proportional to the product of mass and change in temperature. And then the other math trick that we always play in chemistry is if you want to turn something that's a proportionality and make it into an equation, you have to put a constant in there somewhere. So what we do then is say that Q is equal to mass times a constant C, which I'll define here in a second, times the change in temperature delta T. So this is sort of the heat equation, really the only one we're going to use for calculating heat. There's some variations on this that we'll see later, but it's really this one simple equation. Heat is the product of mass times C, which is called heat capacity, and delta T. Okay? So what C is called specific heat capacity. This is the one that involves mass. And so what it is it's the amount of heat that you need to raise 1 gram of substance by 1 degree Celsius. So you're taking the temperature of a substance and raising it by 1 degree Celsius, and its specific heat means for 1 gram of that substance. (1 degree Celsius or 1 Kelvin). One thing we're going to see a lot in this chapter is, now we're dealing with temperature really for the first time. So the two common units for temperature are degrees Celsius and Kelvin. We should recognize that absolute temperatures between the two are different, but the size of 1 degree is the same. So if you're just talking about a change in temperature, a delta T as we do in this equation, 1 degree Celsius is the same temperature change as 1 Kelvin. They're the same size for their individual units, okay? So that's what C is defined as, the amount of heat needed to raise the temperature of 1 gram of substance by 1 degree Celsius. So if we had, 1 gram of water up here at 20 degrees Celsius, and we wanted to put heat into it to raise it up to 21 degrees Celsius, that amount of heat is equal to the specific heat capacity of water. And this value of C is dependent on what substance we're talking about. So it's not a universal constant for everything. It's a constant depending on the substance that you're dealing with. The one we're going to deal with most often is water. We're going to be often measuring heat transfer to aqueous solutions or to water by itself. And so the only heat capacity that you should definitely become familiar with is the heat capacity of water, which is 4.184 joules per gram Kelvin, or gram degree Celsius can be written both ways, because remember that it's per change in temperature, which is the same for Celsius and Kelvin. All right, so that's what it is for water. Every other substance has a different specific heat capacity, so if you need the heat capacity for something else, it would need to be given to you. There's no way to calculate that or know that off the top of your head. Okay, so that's what specific heat capacity is, and then once you have that, and once you know the mass of substance and the temperature change that it undergoes, you can calculate the heat that is either transferred to or from that substance as part of some physical or chemical process. Related to specific heat capacity, we also have molar heat capacity. We don't use this as much, but we should be familiar with it. So as the name implies, molar heat capacity is the amount of heat needed to raise 1 mole of substance by 1 degree instead of 1 gram of substance. All right, so this is molar heat capacity, the amount of heat needed to raise the temperature of 1 mole of substance by 1 degree Celsius. All right, the previous heat capacity we said was per gram. This one is per mole. All right. Abbreviations in this section of the course are not always as clear as they could be, but that's not my decision. That's the powers that be that came up with these abbreviations. So this is also abbreviated as C, but usually we use a capital C for this instead of a lowercase c. Again, the context will tell you which one we're using or which one we need for it. And specific heat capacity is more common, but molar heat capacity we will sometimes use as well. And it's usually abbreviated with a capital C. All right. So capital C, if we want to do it for molar heat capacity for water, we start with a specific heat capacity in grams, so 4.184 just as a number, joules per gram Kelvin. And if we want to convert this to a molar heat capacity, we just need to convert the grams here to moles. I think we know how to do grams to moles now, or at least I hope you do. If you haven't taken the test yet, you should learn very soon. And so it's going to be 18.02 grams in 1 mole. So grams cancel out. That gives us moles in the denominator. And that becomes then 75.40 joules per mole Kelvin. So it's now moles in the denominator instead of grams. So if we have the specific heat capacity of a substance in joules per gram Kelvin, or any unit that involves grams, and we know the molar mass of the substance, which is what this term is here, we can then convert between specific and molar heat capacity as much as we need to. We don't use molar heat capacity as much, but there could be problems here and there where it comes up. Okay? So with that equation, and now with sort of the definitions out of the way, we can start seeing some examples of this. So what we're going to be doing is we'll be running, in a lot of these types of problems, we're running chemical reactions that are either exothermic or endothermic. And if they're exothermic or endothermic, they're going to either release heat or absorb heat, and there's going to be a temperature change associated with that. So we're going to measure that temperature change, and then we're going to calculate heat using that. So if we have an aqueous chemical reaction in 50 milliliters of water, and the temperature raises from 22.31 to 28.37 degrees Celsius, determine the heat absorbed by the water. Okay? So anytime we're calculating heat, it's going to be Q is equal to mc delta T, and here everything is happening in water. So the body that is absorbing the heat is going to be the water that this reaction is occurring in. So we need the mass of the water, we need its heat capacity, and we need the change in temperature. Okay? And one thing to keep in mind when we're doing aqueous chemical reactions like this is that, okay, there are some other things dissolved in the water. We don't even tell you what it is here. But we would typically assume that the heat capacity is just equal to that of water. So even though you have some things dissolved in there, the heat capacity is probably a little bit different. But unless you're told otherwise, just use the heat capacity for pure water itself. So we don't need to do anything to that. We just use the same heat capacity for water that we're going to always use. What we have to do here, though, is find mass of water first. We need that term. And one thing we're going to have to start remembering is that if we have 50 milliliters of water, usually we measure liquids in volume, but for this equation we need mass. How do we convert milliliters of water to grams of water? We could do molarity, but that's a little bit roundabout way of doing it in this case, because it's not really a solution, it's just pure water in this case. So what's the relationship that relates volume and mass? Density, right? Think back way to the origins of your chemistry knowledge. So the basics now. Density of water is 1, so we just multiply by 1 gram per milliliter, or 1 gram per cubic centimeter, whatever the case is. So point being, you don't have to necessarily do this every time because it's trivial, but if you have 50 milliliters of water, you will also have 50 grams of water. So don't be confused by that, because very often we give you volumes of water, but you need masses for these equations. But for water, it's easy because the density is 1. All right, so we have 50 grams of water. That's our mass. The heat capacity of water, as we said, is 4.184 joules per gram Kelvin, or gram degree Celsius. So that's a constant that we're going to use. And then we just have to calculate delta T. Remember, delta anything is final minus initial. So the delta T is T final minus T initial. So our temperature raises from 22.31 to 28.37. So this is our final temperature, and this is our initial here. And so it's going to be 28.37 minus 22.31. So our delta T is 6.06 degrees Celsius. Now, as I said, don't be confused by this, because I'll use them interchangeably. If we're talking about a delta T, a change in temperature, a difference between two temperatures, it's equivalent in Celsius or Kelvin. Okay? The individual temperatures would not be. So we could convert this to Celsius by adding 273. We can convert that to Kelvin by adding 273. We convert that to Kelvin by adding 273. When we subtract the two, we still get the same difference, because we're just changing them by the same amount each time. So we'll use these interchangeably when we're talking about delta T, but don't be confused by that. So we can put that in here as either Kelvin or Celsius, whatever you prefer. And so when we multiply this across, we get 1268 joules, which I didn't specify a unit, but very often we'll convert these to kilojoules, 1.27, just by dividing by 1,000. Okay? So I didn't specify units here, I don't think, but kilojoules is probably more common than joules for these types of problems. All right, so just to reiterate this point down here, delta T will be the same whether we're talking about Celsius or Kelvin. Okay? So we don't need to convert individual temperatures, we just need to find the difference between them to do these types of problems. All right, questions on that? How to use MC delta T? All right, so that's how we determine heat. Let's do one other one here just to see some other variations on this. All right, so here we go. So here we're going to actually determine what the specific heat capacity is. So we have the ability to do that now. So if we have a 1 ounce gold coin, which has a specific heat capacity of 0.129 joules per gram Kelvin, we notice that for this metal it's very low, so metals typically have low heat capacities compared to water. If it absorbs 721 joules of heat, by how much does its temperature increase? Okay, so this is just a variation on the previous one where we're still using the same equation, Q equals MC delta T. Only differences here is this isn't water anymore, so we have a different specific heat capacity, and now we're solving for delta T. So delta T is going to be equal to the heat that's absorbed divided by the product of mass and heat capacity. All right, so we can just start plugging in numbers that we already know. So we see here that the heat is absorbed as 721 joules, so we put that in directly. We do have to be careful with the units a little bit because our heat capacities are typically in joules per gram degree Celsius, so when we're using specific heat capacity in its standard units, we need the heat to also be in joules, not kilojoules if it was given to us there. So it's already in the right units, and then we have to do the product of mass and specific heat capacity. Specific heat capacity for this one is 0.129 joules per gram Kelvin, but we need to find the mass. The mass is given to us in ounces, which is not the standard unit that we need for this heat capacity, so we need to convert the mass to grams. So we have 1 ounce of gold, and 1 ounce is equal to 28.35 grams. That's not a conversion factor you would have to know off the top of your head. We're giving it to you here. 28.35 grams is going to be then our mass in the correct units of grams. So we put that here, 28.35, and we end up with 197 Kelvin when we divide. So with this MC delta T equation, we could either have you calculate heat like we did last time, or we could solve for any of these other ones if we give you, just one as an unknown. So be familiar with all that, and really the only trick to this is make sure you have the units right so that everything works out. Heat in joules, mass in grams, and then we get Kelvin as our answer. That's our delta T, so that could also be written as 197 degrees Celsius as well. Okay? Questions? All right, so that goes over sort of the basics of calculating heat. Now, where we're really going to use this is, not often are we going to just, calculate the heat of something and just be done with that. We're going to use it to measure enthalpy changes or energy changes for chemical reactions. And so the way we do that, or we can do some other things with it as well, it's not just limited to that, is with what's called a calorimeter. So this is sort of the laboratory approach of how do we apply this Q equals MC delta T equation to teach us things about chemical substances, either their physical properties or the delta H or delta E of a chemical reaction that they're participating in. We use what's called a calorimeter, which is a device. All right. So a calorimeter is a device used to measure heat. And what it does for us is it contains the surroundings. So if we have some sort of chemical or physical process happening that involves heat transfer, as we talked about when we were first introducing this, if the surroundings are losing heat or gaining heat, or whatever the case is, but let's say they're losing heat, it's easier to think about it that way. If the system is losing heat, the chemical reaction is giving off heat, that heat could in principle go to the entire surroundings, which is the whole universe. And that's not a very useful thing for us to do experimentally to try to keep track of all that heat throughout the entire universe. So what a calorimeter does is it contains the surroundings by insulating them. So basically it's a really well-insulated container so that whenever heat is released by the chemical reaction or is absorbed by the chemical reaction, it's contained in this relatively small device as opposed to just dissipating everywhere and just spreading out the whole room. So it contains the surroundings so that you can very easily track and measure the heat as opposed to having it go everywhere. All right, so that's what a calorimeter does. Usually they're filled with water. So water would be the substance inside the calorimeter that's absorbing the heat. So we use the Q equals MC delta T as part of that to calculate the heat that's absorbed by the water. But then on the outside of the bath of water is really well insulated so that you don't have heat going into the water and then also being spread everywhere else. It stays inside of that calorimeter and is really well contained so that we can accurately measure the temperature change and accurately measure the heat without heat being spread out and distributed all throughout the surroundings that you're in. Okay? So there are a few different scenarios here. So we're going to basically, in a calorimetry type experiment or problem like we're going to do, we're going to measure the heat that's associated with the calorimeter. Q-cals, I've abbreviated it here, which is the heat that's either absorbed by the calorimeter or the heat that's released by the calorimeter to the system that you're studying. And there's 3 scenarios for determining this. So it really depends on how the problem is set up and how rigorous you want to be experimentally if you're doing this in the lab. So one situation is that we just tell you how much water is in the calorimeter and nothing else. So we tell you that the water is filled, the calorimeter is filled with this much water, and you want to calculate heat. Then all you need to do is just use the same equation, MC delta T, where all we care about is now the mass of water. So again, it really depends on what information is given to you. That should be lowercase c if I'm being careful with capitalization here. And again, the heat capacity of water is at 4.184. So if all we're telling you in the problem is that you have a calorimeter filled with this much water and the temperature changes by this much as part of the reaction, whatever's happening, you just use MC delta T and you just have to use the mass of water that's present to be able to calculate heat. Now the other possibility is that we are only given the heat capacity, or what's sometimes called the total heat capacity of the calorimeter. Okay? So in this situation, we don't know how much water is in the calorimeter. We just know the total heat capacity of the whole thing. The calorimeter has water in it, it has containers that hold the water, it has a thermometer to measure temperature, it has all these things in it, and we just measure the total heat capacity. And in this situation, the heat is just the product of the two. The total heat capacity, again, capital C can mean molar heat capacity or it can mean total heat capacity, and it's just the product of that times delta T. So here we don't know the masses of all the substances in the calorimeter. We don't know how much water is in there. We don't know what other substances make up the calorimeter. We just know the total heat capacity, which typically experimentally what you do is you measure it beforehand. So you do some known chemical reaction inside the calorimeter with some known heat transfer. You calculate the heat capacity, you sort of standardize it, and then you measure some unknown chemical reaction and use this to calculate heat. So that's the simplest way to do it, perhaps. The third scenario is, let's say we give you the amount of water in the calorimeter and we tell you the heat capacity of the empty calorimeter. So this time you have the amount of water, so you know that the water is going to be absorbing heat, and you know the heat capacity of the calorimeter itself, which will also absorb some of the heat. So in this case, the heat for the calorimeter, I'll put that same abbreviation so I don't confuse you here. The heat for the calorimeter is the product of the heat capacity of the calorimeter itself times delta T plus the mass of the water in the calorimeter times its heat capacity times delta T. So this is really the most rigorous and accurate way to do it, because we're accounting for the heat that's absorbed both by the water in the calorimeter and the heat that's absorbed by the calorimeter itself. But sometimes we make assumptions or simplify things and only focus on one of these. So we'll go through these different situations as we do all the different practice problems we're going to go through, both today in class as well as later on in homework assignments and things like that. But these are the three possible situations. It really depends on what information you have about the calorimeter, how you actually calculate Q. Okay? So we'll see that as we go through. All right, so let's give some more information about calorimeters, a little bit more about what they look like. So the first type of calorimeter we're going to talk about is a constant pressure calorimeter. So these are vented, so that means that the pressure doesn't build up as the chemical reaction is happening or as heat is being generated. You don't build up pressure, you vent that to the surroundings. So these are vented. The simplest way to do it is with just a coffee cup. So if you guys do this in the lab, you'll probably use a very similar calorimeter like this, which is just a coffee cup or a styrofoam cup or a thermos of some sort that insulates the surroundings. And these types of calorimeters are especially useful if you're doing a reaction in solution or liquid phase. Okay? So if you have a chemical reaction occurring in a liquid, as typically in solution, or if you're measuring some other physical process involving a liquid, this is the type of calorimeter that's most useful for that. You can do it for solid phase as well. These aren't very good for gas phase things because, as we said, they're vented, so whatever gases you generate would escape to the surroundings, and that would be potentially problematic for the accuracy of your measurement. But for things that just involve solids and liquids or some combination of those two. So the first application of calorimetry we're going to talk about is not actually for determining a delta H or a delta E, it's just for measuring a heat capacity. So you might be wondering, well, we have specific heat capacity for all these different substances. We know the one for water, we saw the one earlier for gold. How actually do we measure that? And you can do that using calorimetry. So what you do is you heat up the solid to some temperature. You place it into water in a calorimeter that's colder than that. Now this is specifically for substances that don't dissolve in water. So let's say we want to determine the specific heat capacity of a piece of copper or a piece of gold or something that doesn't dissolve in water, which is what we're talking about here. This is how we do it. We take the solid, we heat it up to a higher temperature, and we drop it in the calorimeter. And what we should recognize is what's going to happen is that the object is going to transfer its heat to the water. So what we measure then is the initial and final temperatures. For both the solid and the water. So they're going to have the same final temperature because the heat transfer stops when the two substances, the object and the water that it's in, reach the same temperature, but they're going to have two different initial temperatures. We're going to measure both of those. And then the relationship that we use is we have to recognize that the heat that's released or absorbed by the solid, the heat that's released by the solid, is equal to the heat that's absorbed by the water. However, we have to recognize also that one of these, the object that's starting out at the higher temperature, is releasing heat to the water, while the water is absorbing heat. So they're going to have two different signs for Q. One's going to be positive, one's going to be negative. So we can't just set the two equal to each other. We have to put a negative sign on one side of the equation. It doesn't matter which side, but one of those sides is put a minus sign. So the heat is equal in magnitude. The amount of heat that's lost by the object is equal in magnitude to the amount of heat that's absorbed by the water, but they have opposite signs because, again, if it's releasing heat, it's negative. If it's absorbing heat, it's positive. All right, so that's the equation. And then what we do then is use MC delta T on both sides of these equations. Again, keeping the minus sign on one side to make sure they're actually equal to each other. And the mass of whatever solid we're measuring, heat capacity, times its heat capacity, times the change in temperature, is equal to the mass of water, heat capacity of water, and delta T for the water. All right, so the heat that is lost by the hot object is the heat that is absorbed by the water. And usually in these types of problems, well, not always, but usually what we're doing is we're going to solve for the heat capacity of the solid object that we're measuring, which is just going to be rearranging this equation. But again, you don't have to necessarily memorize this equation that I'm writing here because it just comes from the equation for heat, which is MC delta T, and setting the two equal to each other but opposite in sign. All right, so that's how we can use calorimetry to measure heat capacities. We measure the amount of heat that's transferred between the object and the water, and then we relate those two to each other and solve for the unknown, which is our heat capacity. Because we're going to know how much water we use is the mass of water. We're going to measure the mass of the solid. Heat capacity of water is a constant. We measure the two delta T's, and with all that information, we can get heat capacity. All right, so let's see how that works in practice. So let's say we take a 10-gram sample of a solid, heat it to 75 degrees Celsius, and then place it into a calorimeter that has 50 grams of water initially at 25 degrees Celsius. The temperature of the water changes to 26.64 degrees Celsius. What is the specific heat capacity of the solid? So the first thing we have to recognize here is that in this problem, we're talking about a calorimeter. We only know the mass of the water in the calorimeter. We don't know the heat capacity of the calorimeter itself. We don't know the total heat capacity. So all we have to worry about is the mass of the water and its heat capacity. And so just like we saw in the last one, we set the two equal to each other. The heat that's lost by the solid is equal but opposite to the heat that's gained by the water. And I'll write it the same way as last time. I think in hindsight it makes more sense to put the minus sign on this side of the equation, but it doesn't matter. You can put it on either side. It's just one negative sign to make sure that one minus sign to make sure that the two are actually equal. And what we're solving for here is the specific heat capacity of the solid, which is C. So we just rearrange and we get, as we said, mass of water, heat capacity of water, delta T for the water on top, that's the heat for water, with a minus sign in front, divided by the mass of the solid and its heat capacity, delta T. All right, so we just start plugging in the things we know and figure out what we don't know. So the mass of water, we're told, is 50 grams. So we know the mass of water. That's this first term here. Heat capacity of water, we're telling you here, but you should know this one just to make sure you always have it when you need it. 4.184. We don't know the delta T's right away. We'll get those in a second. And then in the denominator, we know the mass of the solid is, we said we had 10 grams of the solid, so that's our mass for the other object. And we're solving for its heat capacity. We need its delta T as well. So the only two terms that we don't directly have from the information in the problem are the delta T terms, which are not going to be the same for the two, by the way. So if we think about the delta T's, we said that the delta T for water is final minus initial. So we said that the temperature of the water changes to 26.64, so that's our final temperature. The initial temperature of the water was 25, so its initial temperature is 25, which means the change in temperature is 1.64 degrees Celsius or 1.64 Kelvin. Remember that the change in temperature can be written either way. All right, so that's our delta T for water is 1.64 Kelvin. For the solid, we're again going to do final minus initial to find its delta T, what is the final temperature for the solid? Is that told to us directly here? Anybody see it in the problem? Alright, so there's no number in the problem that tells us what the final temperature of the solid is, but remember, when we place two objects in contact with each other and there's heat transfer, the heat transfer stops once the two temperatures are equal. So the final temperature of both the object and the water will be the same. So the final temperature for both will be the same. It's going to be 26.64. So they have the same final temperature, but the initial temperature of the solid, the object that we're placing in the calorimeter, was different. That's this number here, 75. So one of the, whenever you place two different objects in contact with each other with two different temperatures, one of them warms up, one of them cools down, and they stop when they have the same temperature. So that's exactly the concept here. So we started at 75.0 degrees Celsius. So this is going to be final minus initial for the solid, which is minus 48.36 or minus 48.36 Kelvin, so we can keep everything consistent. So we're going to put that into here, minus 48.36 for the delta T for the solid. And then I don't have room to write it, but down here, what we'll get is that the heat capacity is equal to 0.709 joules per gram Kelvin. So that's numerically what we get when we take these, multiply them together, divide by that. And so that's the heat capacity of our unknown object here. So when we're solving for heat capacity, again, the heat that's lost by the object is equal to the heat gained by the liquid, equal and opposite. We set them equal to each other, solve for our unknown, which in this case is heat capacity. All right, questions on that? All right, so the other thing that we can do with calorimetry is determine enthalpy changes, delta H. Okay? So in this setup here, did I lose something? All right, so if we're going to measure delta H using a calorimeter, remember that delta H is equal to delta E plus P delta V. And the way that we measure delta H then is by measuring the heat at constant pressure. So in a constant pressure calorimeter, if we measure heat for some sort of chemical reaction that's happening, that will directly give us delta H. Okay? So delta H will be directly measured by a constant pressure calorimeter. All right? So as we said in these types of problems, the first thing is to determine the heat for the calorimeter using MC delta T primarily. So the heat for the calorimeter is equal to the mass of water in the calorimeter, heat capacity of water times delta T. So this is the heat that's absorbed by the water, plus the total heat capacity of the calorimeter itself times delta T. So this is the heat that's absorbed by the calorimeter. And as I said, when you're doing problems, whether you use one of these two terms or both of these two terms depends on the information we give you in the problem. But the first step is going to always be to calculate the heat for the calorimeter, which is some combination of MC delta T for the water in the calorimeter plus the heat capacity of the calorimeter itself times delta T. So you need those two things to calculate it. Depending on what we give you, you'll use one of them or both of them in different cases. And then what we do is we determine delta H. So once we have that, the heat for the reaction is just equal to the negative of the heat for the calorimeter. Okay? So if heat is released by the reaction, it's absorbed by the calorimeter, or vice versa. So again, the two are equal to each other but opposite in sign. Whatever heat is released from the reaction will be absorbed by the calorimeter. But the value that we measure depends on the scale of the reaction. Okay? All right, and that should hopefully make sense. If we burn one drop of gasoline up at the front of the room, we're going to release a little bit of heat. If we burn a gallon of gasoline at the front of the room, we should probably run for our lives. We're going to release a lot of heat and cause a lot of damage. So again, the amount of heat that you release in a chemical reaction depends on how much substance is participating in that reaction. So if you measure heat this way using a calorimeter, the value that you get for heat of reaction, Q reaction here, is dependent on how much substance is involved in the reaction. What's more interesting for us is to calculate delta H in terms of usually moles of product. So we're going to take the heat of reaction and we're going to normalize it to how many moles of substance in the reaction, usually a product that we're forming that we're interested in. But there are different ways of doing this. We'll learn sort of more precisely how to deal with this in a second. But the last step is typically going to be taking the heat for the reaction and dividing it by moles of substance so that it's heat per mole of substance to make it a more useful quantity as opposed to just some random heat value associated with that reaction that you did. Okay? All right, so let's see how we do this then for a couple example problems. Okay, so let's say we have a 1 gram sample of ammonium chloride. We add it to a calorimeter with 50 milliliters of water, and the initial temperature is 22.3 Celsius. If the final temperature is 20.98 degrees Celsius, what is the enthalpy of dissolution for ammonium chloride in kilojoules per mole? So here we're just dissolving a compound in water and trying to figure out what is the enthalpy change associated with dissolving that compound in water. So we have some assumptions here with solution density, heat capacity, all that stuff. So the process that we're studying here is taking solid ammonium chloride, adding it to water. So we'll put water above the arrow to indicate that we're just adding it to water, and we're making aqueous ammonium chloride as a solution. And we want to measure the delta H for this process per 1 mole of ammonium chloride. So again, we want delta H in kilojoules per mole. So delta H per mole of substance, not just for any random amount of substance. So the first step, as I said, is to calculate the heat for the calorimeter, which is going to be the mass of water in the calorimeter times heat capacity of water times delta T, plus the heat capacity of the calorimeter itself times delta T. Now, if we look at this problem here, did I give you the heat capacity of the calorimeter? Does anybody see it anywhere? We have the amount of water, we have the heat capacity of water, but we don't have anything about the calorimeter, so that means we just ignore this term. So as I said, there's 2 terms you have to consider when calculating heat for a calorimeter, but depending on what we give you in the problem, you may or may not have to use both of those. Okay? So here we don't know anything about the calorimeter itself, so we just need to use MC delta T for water, and all that information we already have. So we said 50 milliliters of water. The mass of water will then be 50 grams because it's a density of 1. So we have 50 grams of water. The heat capacity is 4.184 for water. And we said that we have to find the temperature change for water. So delta T is going to be equal to final minus initial. So the final temperature is 20.98 Celsius. The initial temperature was 22.30. So our temperature change is negative 1.32. Celsius or Kelvin. So we plug that in for our delta T, and as usual, my poor planning doesn't give me room to write it, but what we get is negative 276 joules. Okay? So what that means is that the water is releasing or losing 276 joules of heat because it's a negative here. Okay? So that's the heat for the calorimeter, which in this case is just water, is negative 276 joules. And then, as we said, the next step is to realize that this heat is equal to the negative of the heat of a reaction. So the heat for the reaction, in this case the dissolution, the dissolving process, is equal to negative Q for the calorimeter, which is equal to plus 276 joules. Okay? So if we calculate a negative Q for the calorimeter, that means whatever process we're studying has a positive Q, because again, they're equal and opposite to each other. So that means the heat for this is 276 joules, and then what we want is delta H, which is heat of reaction per mole of substance. So we said that the heat of the reaction is plus 276 joules. We're going to normalize that to the moles of substance that are involved. So we're using 1 gram of ammonium chloride, so we should remember then that to find moles of ammonium chloride, we just have to use molar mass. So we have 1 gram. And 1 mole of ammonium chloride, we said the molar mass is 53.49. So the moles of substance that we have is 0.0187. And so then we're going to divide the heat of reaction by 0.0187 moles to get the heat of reaction per mole. What we want, though, is kilojoules per mole. So we have one more step here, which is to multiply this by 1 kilojoule over 1,000 joules to get it into the right units of kilojoules per mole. So always pay close attention to units in these problems, as I said. So that gives us kilojoules per mole, and it comes out to a positive number, 14.8. So this is an endothermic process, positive delta H. And we see that the temperature of the surroundings, which is the temperature of the calorimeter, went down as it should for an endothermic process as we talked about earlier. So this is how we use a calorimeter to calculate a delta H, this time for just dissolving something. Any questions on this one? All right, we can also do it for an actual reaction, in this case, an acid-base reaction. So let's say we take 50 milliliters of 1 molar HCl in a constant pressure calorimeter. We add 1.6 grams of solid NaOH, and the reaction increases by 7.27 Celsius. What is the heat of reaction in kilojoules per mole of water formed? We have, again, the same assumptions as last time about solution density, heat capacity, all that stuff. So this time we're doing an actual chemical reaction. So we have HCl plus NaOH forming water and NaCl, so typical acid-base equation that we should be familiar with from Chapter 6. So that's the reaction that's taking place in the calorimeter. Separate from all of that, we can calculate the heat for the calorimeter itself, or sorry, I'll use the same abbreviation, Q for the calorimeter, which is equal to mass of water, heat capacity of water, times delta T for the water, plus the heat capacity of the calorimeter itself times delta T. Once again, we don't tell you the heat capacity of the calorimeter, we just tell you the amount of water that we're using, and so we don't have to worry about that term. Now the part that's a little bit tricky here is that, well, actually not in this one, in the next one, sorry. In this problem we have, again, 50 milliliters of solution. We're assuming that it's still a density of 1 even though it's a solution, and same heat capacity. So again, we assume 50 grams of water because that's the amount of aqueous solution in the calorimeter, and we approximate that as the same as the amount of water. So we have 50 grams with a heat capacity of 4.184. And we're telling you directly in this problem that the temperature increases by 7.27 degrees Celsius, which means that the delta T is plus 7.27. So if we're telling you directly how much the temperature changes, you don't have to calculate delta T. That's provided for us directly. So 7.27. So this time we have 1521. So 1521 joules of heat absorbed by the calorimeter, absorbed by the water in the calorimeter. But then what we're looking for is delta H in kilojoules per mole of water formed. So we have to figure out how much water is actually formed in this reaction and normalize to that amount. So this, as annoying as it sounds, but I guess it's a good review for those of you that haven't taken the test yet, it's kind of like a limiting reactant problem. Because we have two reactants, HCl and NaOH, we're trying to figure out how much water forms as a product so that we can normalize our delta H per mole of water. So we have to determine how much water forms. So the moles of HCl, we have 50 milliliters of HCl solution. That's that number there. The molarity is 1, so we have 1 mole of HCl per 1,000 milliliters. So we have 0.0500 moles of HCl. And then if we do moles of the other reactant, which is NaOH, and this time we told you we added it as a solid, 1.60 grams. So for that substance, we're going to use mass to mole calculation to find moles of NaOH. Molar mass is 40, as we gave you right here. So we have 0.0400 moles of NaOH. These react in a 1-to-1 ratio, so the one that has the fewer number of moles is going to be the limiting reactant. It's a 1-to-1 ratio between HCl and NaOH. So NaOH is going to limit how much water forms. We only have 0.04 moles of that. If we only have 0.04 moles of NaOH, we can only form 0.040 moles of water. So I'm going to skip that calculation because it's fairly trivial, but we have this many moles of limiting reactant. They react in a 1-to-1 ratio and form the same number of moles of product, so that's going to be the moles of water that forms. So then finally our delta H is going to be heat of reaction divided by moles of water that form. which is equal to the negative heat for the calorimeter, Qcal, divided by moles of water. So as we said, the heat for the calorimeter is 1521 joules. So we're going to put that in as minus 1521 for the heat of reaction. And then we have 0.0400 moles of limiting reactant, meaning we form 0.04 moles of product. And then we have to multiply by 1 over 1,000 to get that into kilojoules, as we specified here. So we divide heat by the moles of substance to convert to kilojoules, and we get minus 38.0 kilojoules per mole. All right, so this one is an exothermic reaction. Delta H is negative. Temperature of the surroundings increases, and we have to go through those steps to calculate it. So there's a few different steps here, but they're going to be very similar for all these problems. Calculate heat first, relate that to moles of substance. Let's see what we have left. All right, we'll try to go through this. I don't know if we'll get through the whole thing, but we'll get through most of this. All right, so now we're doing a precipitation reaction. So we have just another variation on the same theme. All right, so we have 50 milliliters of 0.1 molar barium nitrate. We combine that with 40 milliliters of 0.1 molar sodium sulfate. The temperature increases by 0.383 degrees Celsius. And so we're going to go through a step-by-step process to figure out delta H for this reaction, okay? So we'll just do it one step at a time here to close this out. And I encourage you, as I say here, to try it on your own when you get home to make sure you understand all these steps. So the first step is to determine the heat for the calorimeter. And for that, we don't need to know anything about the amounts of substances that are reacting. So here we're dealing with aqueous solutions. A common mistake that people make is they want to put the mass of the substances in. We don't need the mass of the substances that are reacting. We just need the mass of the water in the calorimeter. That's all, the only mass we need to calculate heat. So we need that. And as I said, there will sometimes, none of the ones that I gave you today, but you'll see this on homework assignments, you'll sometimes have a second term associated with the calorimeter itself. We, again, don't have that here. So we have to figure out then just the heat that's absorbed by the water to find heat for the calorimeter. So what we have to be careful with here is how much water is in the calorimeter. So we're starting with a 50 milliliter solution. We're adding to that 40 milliliter solution. So when the reaction occurs, we have a total of 90 milliliters inside the calorimeter. Okay, because we have 50 milliliters of one reactant, 40 milliliters of another reactant, and we're combining those two together. So the total amount of water in the calorimeter that's going to absorb all the heat from the reaction is actually 90. So if it's 90 milliliters, that means we have 90 grams as well, because our mass of water is, we started with 50 grams of water from one of our reactants, but we added to that another reactant that was containing 40 milliliters of water. So in total, we have 90 grams of water if we mix two solutions, mixing two solutions together in this case, okay? Because those two things don't react with each other until the two solutions are in contact. Once the solutions are mixed together, any heat that is generated is going to be absorbed by the full amount of water, not just by one of them. So we're going to use 90 grams as our mass of water, same heat capacity of water that we always use, 4.184. And then delta T here, we said increases by 0.383. So it's going to be a positive 0.383 for our delta T. And so when we multiply those, we get 144 joules. So the heat absorbed by calorimeter is 144, positive number because temperature is increasing. All right, so that's step one. Step two in this case is determine the moles of precipitate formed. So as I said, when we're doing delta H problems, we typically normalize it for some mole of substance that's involved. Here we want to find how many moles of precipitate are formed. This is, again, a review of Chapter 6. Since I'm running low on time, I'll skip the calculation here. I'll write it out in the notes before I post them. But what we would find in this case is that the reaction that we're doing here is barium nitrate plus sodium sulfate. And the two products we get are barium sulfate and sodium nitrate. So we should recognize that this is aqueous, it's soluble, but this is going to be our precipitate, barium sulfate. So sulfates are insoluble for the heavier group 2 elements, barium, strontium, and calcium. So that's our precipitate. We need some coefficients to totally balance this. But we identify that this is our precipitate. We go through the limiting reagent calculations figure out which our limiting reagent is, and what we finally get to, which I'll work out in the notes before I post them, is that the moles of barium sulfate that we form as a precipitate is equal to 0.00400. All right, so that's how many moles of barium sulfate we form as a product. I'll go through the calculations before I post the notes. And then finally, the last step is to determine delta H in kilojoules per mole of that product. So delta H, again, is going to be the heat of reaction divided by the moles of product that we form. We're going to normalize to the amount of substance that's involved. All right, we saw that heat of reaction is just given by the negative heat for the calorimeter. In the first step, we saw that the heat for the calorimeter was plus 144 joules. That means the heat of reaction is minus 144. So it's minus 144 for heat of reaction. Minus 144 joules. As we said in the last step, which I didn't go through in detail, we found that there's 0.00400 moles of product formed. So that's going to be what we divide by. We want it in kilojoules per mole. So we have to then convert joules into kilojoules like we usually do. So 1 kilojoule is 1,000 joules. And what we end up with is minus 36.0 kilojoules per mole. So that means for every mole of barium sulfate we form, we also release minus 36 kilojoules of heat. We release 36 kilojoules of heat. So that means choice D would be the correct one here. All right. So any questions before we wrap this up? All right. I will update the notes, and I will also fix the homework review tonight. But other than that, I'll see you guys either on Wednesday in class or before that if you have any last questions about the exam.